We saw last class that springs conserve mechanical energy, but also that when we had a mass moving up and down in a spring, it was complicated because of the fact that then we've got three different forms of energy to keep track of: spring energy, height energy, and motion energy. It turns out there's an easier way. If we agree that we're going to measure the stretch distance not from the end of the spring, but from equilibrium, then things get easier. So we said last time, here's an unstretched spring. You have to measure the stretch distance from that point. That's the real stretch of the spring. But we remember for horizontal motion, the equilibrium point was a point where there was no energy stretched in the spring. If we just treat this like a horizontal spring and measure the distance from the equilibrium point, let's call it x prime, right? Here was the equilibrium point right here. Then it turns out that you can ignore that height energy because the only effect of gravity is to stretch the spring to this new location. So it turns out that if you use x prime instead of x, then you can ignore gravitational potential energy. So this is going to make the equations a little bit easier, because now there's only two forms of energy. So really, we're sort of looking at it sideways with this is the equilibrium point, right? You remember horizontal spring, back and forth and back and forth. The sum of kinetic and elastic energy was a constant. Well, let's look at a couple of problems we already did. So we hung a mass from a spring. So here, it stretched the spring down to the equilibrium point. We pulled it down, we let it go. We wanted to know how fast is it going when it comes back to equilibrium. Well, if we're measuring our distance from equilibrium, we're told we pulled it 10 centimeters away. So x prime is the distance from equilibrium. The real distance x would have to be measured from this point up here. But x prime we just measured from equilibrium. Well, it's 0.1 meters here, and then back at equilibrium it's 0. So when we say energy at the beginning plus work by non-conservative forces equals energy at the end, now there's just two forms of energy. There's kinetic and what we're going to call primed spring energy. Now at release, it's at rest, so there's no speed there. Here, the stretch was equal to 0.1. Spring is conserved energy, so that's 0. Here, we're back at equilibrium, so that term is 0, and then the speed is the unknown. So our energy equation ends up looking as follows. We've got primed spring energy at the beginning, and then at the end, just kinetic energy. Now that is so much easier than our previous equation, and yet it gives the same answer. So the K value is 750 and the mass is 10. So that's 750 newtons per meter. It's a newton per meter. And so you can verify, whoops, that's 0.1 meters squared. You can verify that this is going to give the same answer for V, which is 0.866 meters per second. And the equation's obviously a lot simpler. Now, this is a technique that works, but it does have to, or it does lead us to sort of make uncomfortable statements. For instance, you have to pretend that a spring is unstretched at equilibrium, because there's no distance from equilibrium. But of course, we know that it is really stretched, right, by an amount like mg over k. You also have to pretend that when the spring is unstretched, when the real stretch is 0, because it's not at equilibrium, say a vertical spring, that there is actually some primed spring energy in that. That comes into play in doing this next example. So we did this one previously. And so we had a mass hitting a spring. Now that spring is initially uncompressed, so it's not at the equilibrium point. If you do the equilibrium calculation, you see we're actually 9.8 centimeters away from equilibrium. So even though the real x is 0 here, as we stated earlier, the x prime is this 9.8 centimeters. Now it moves down and stops, and then the unknown is how far it went from the equilibrium point. Well, when we set up the energy equation, at the initial point, there is both kinetic motion energy and prime spring energy. Mechanical energy is conserved. At the bottom it stops, so there's no kinetic, there's just prime spring energy. So with our formulas, this is going to be x prime initial squared, and this is 1/2 k. We could just call it a squared, that distance a, the maximum distance from equilibrium. So we put in the, what was that speed? 5 meters per second. And 1,000, and then we were 0.098 meters above the equilibrium point initially. That's meter right there. And then you can solve that for the distance a. Now, we had previously found the total stretch of the spring as being about 60 centimeters. When you calculate A, you're going to get about 51 centimeters. And then the 51 centimeters that you get for A, when you add the 9.8 centimeters, you get back to the original answer we had before. So I think this is about 50 point something, almost 51 centimeters. Okay, so the fact that those are the same as the answers we got before means that yes, this works. Next to the notes package, we have 2 problems for you to do. Okay, try setting this up. Example 3, believe it or not, is just like example 1 that we just did together. Example 4 is just like example 2. So that's pretty much just repeating it, doing it on your own to get it straight, and try using the x prime technique for both of them just because it's easier. With x prime, you don't have to worry about height energy. It's just like a horizontal spring. You're just measuring the distance x prime from equilibrium. So that's the first topic for today, a simpler coordinate system for doing spring calculations. The next task is to watch the simulation on the Moodle site and answer some basic questions about it in terms of watching this mass move back and forth on the spring and then answering questions about how its velocity is changing over time, how its position is changing over time, and the force that acts on it over time. So that's on the Moodle site. Watch that and then answer the attached questions. We'll close our pre-lecture now just by talking a little bit about the next key problem. So we've talked about elastic energy. We're now going to move on and talk about oscillations. In particular, we're going to focus in on a key topic in physics, which is simple harmonic motion. Now, harmonic just refers to a motion that repeats itself over and over and over again. That could be, an ideal ball bouncing on a floor. It could be a planet revolving around the sun, or it could be a mass moving on a spring or a pendulum swinging back and forth. Now, not all of those are what we call simple harmonic motion. Simple harmonic motion occurs when we have a force that gets bigger the further away you get away from an equilibrium point. So something that looks like a force varies with the distance from equilibrium by some constant. So we see that the spring force is a natural for that. If we write out Newton's second law, then the sum of the forces is kx, and that's got to equal ma. Well, we see that the acceleration depends on where the object is, so it's a non-constant acceleration. This makes it a more difficult problem. The other thing is, because the force is back towards equilibrium, there's usually a minus sign written in there because this is a vector equation. Now, as you are learning in your calculus courses, acceleration is the rate of change of velocity, or what we call the second derivative of position. I'll drop the vector signs for simplicity now. And so we're looking for a function x that satisfies this equation. So we're looking for a function x so that when we put it in there, if you multiply the mass by the second derivative of that function, you get the original function multiplied by some other constant. This is an example of what we call in physics a differential equation. And we haven't had to do this yet because all of our other forces were constants, and you could just get the acceleration and then use the constant acceleration equations. Okay? It's not going to work here because the acceleration is not constant. Okay? We have to do a calculus solution. Now, solving this differential equation requires a little bit of math. We're going to proceed in a more simple way. We're going to say, let's just show that this is the answer. So we're going to show that when we put this in for x on both sides that it works. So we're going to show that the mass times the second derivative of this cosine function gives itself the cosine function times a constant. Okay, so let's work on this side here, and let's do a couple of derivatives. Okay. Now, first of all, let's do the first derivative. Well, that'll be the velocity. So the derivative of a cosine function is a negative sine function. And then you have to multiply by the derivative of the inside. That's the chain rule. Now, this is a bit algebraic here. What's the derivative of this thing inside? Well, omega is a constant, delta is a constant. So the derivative of delta is just 0. And then for the derivative of omega t, you pull out the omega, and then it's just the derivative of t, which is just 1. So you've got omega times 1, or just omega. So for that first derivative then, we get minus a omega sine of omega t plus delta. Now that's just the first derivative. We want the second derivative of position because that's the acceleration. So we have to differentiate again. So let's do that. We're going to differentiate now minus a omega sine of omega t plus delta. So we'll do it in 2 steps. First of all, we have to do the derivative of a negative sine function. Well, the derivative of a negative sine function is just a negative cosine function. But then by the chain rule, we have to multiply by the derivative of the inside. And we said earlier that the derivative of the inside was just omega. So we get omega squared, I'll pull that, or minus omega squared, I'll pull that out front, times a cosine omega t plus delta. So that's the acceleration function. So what we wanted, I'll remind you, was to show that when you take the acceleration and multiply by mass, you get back the original function. Well, we've shown that almost exactly. So if we want mass times this second derivative here, I'm not going to write the argument just for simplicity, we want that to equal negative k times the x function, which again was cos omega t plus delta. So we see that we've got the functional term, the a cos of omega t plus delta is the same on both sides. And so that's sort of taken care of. So we can see that we've got a solution here, provided that m omega squared equals k. And I'm canceling out the 2 minus signs. Or, dividing by m, taking the square root, omega is root k over m. So, the motion of a mass in harmonic motion, say for instance a mass on a spring, is given by a function like this, where omega is the root of the k constant divided by the mass of the object. So this is the equation of motion for simple harmonic motion. Now, a cosine function, when you graph it, sort of looks like this, right? And there's 3 parameters there. A is the amplitude, and that is measured in meters or centimeters. Any length unit is fine. And that's just how far do you get from equilibrium. It's the maximum distance from equilibrium. It's always positive. Next, omega. It's a Greek letter omega. It's not a W. As we've seen earlier, it has units of radians per second. That works because you want to have radians inside the cosine term, and radians per second times seconds will give you radians. And you want radians so that you could take the cosine of it. Now, we're going to see that determines the rate of vibration, how quickly the object is vibrating back and forth on the spring, how quickly the pendulum is swinging back and forth and back and forth. That's the variable omega. The last one up here, this is a Greek letter delta, and it has to be in radians so that you can take the cosine of it. That's called the initial phase angle, and it's just related to the start point of the vibration. So if you imagine a pendulum, say a mass on a string, you could release that pendulum at a number of different places. You could release it, say, on the extreme left or on the extreme right. You could also let it hang straight down and give it a whack. And those vibrations could all be basically the same amplitude and rate of vibration. They're just different in terms of where they started off. So these three parameters characterize the motion for, say, a pendulum or a mass on a spring. And we want to learn a little bit more about what these variables tell us and how we're going to calculate them and look at some examples of harmonic motion. But this concludes our pre-lecture, and this puts us in a position where we can come to class and dive straight into our study.